The title of this presentation is Quantum Inverse Scattering Type Arguments for Vertex Models. To begin with the presentation overview, we'll be introducing the six-vertex model, the R matrix, and a Hamiltonian flow. And from these objects, we'll be interested in drawing upon similarities for computing the action angle variables from a method that was originally executed in seminal work for the nonlinear Schrodinger's equations, which also has some connections to Hamiltonian formulation for another partial differential equation of interest. And we'll also be discussing how aspects of a conjecture for integrability of the Hamiltonian flow for the inhomogeneous six-vertex model that was raised by Keating, Reshetikhin, and Sridhar can be applied to the higher dimensional, three-dimensional six-vertex model, and how we can begin to look to the lower dimensional case to have some type of ideas about how we could begin understanding how some information in lower dimensions can help us understand a lot of more complicated structures and also computations with the Poisson bracket of a three-dimensional transfer matrix, which we can define more precisely in some later talks. And in doing this, we'll be demonstrating how notions of the quantum inverse scattering approach change with additional assumptions on the R matrix and the L operator. And so we'll want to refer to the following background for computing the action angle variables from this reference, which was given from the fact that the authors investigate some notion of Poisson structure and action angle variables for the Kamasa-Home equation. And it's going to be relating to the discussion of the six-vertex model, because even though the six-vertex model, it's a model in mathematical physics and discrete probability, which isn't defined in terms of an initial value problem or a class of initial data that someone can pass for solving a partial differential equation of interest like the Kamasa-Home equation. But it's helpful because it involves and demonstrates a lot of characteristics of the quantum inverse scattering approach, which we can be interested in applying in more complicated arguments and to study a more complicated three-dimensional structure of the six-vertex model or the 20-vertex model on the triangular lattice. And so from this reference, they describe some background in terms of just the statement of the partial differential equation itself. So this Kamasa-Home equation is given by the first partial derivative with respect to time of the solution, and there are also other terms, namely mixed partial derivatives, as well as taking a frequency term omega and multiplying it to the first derivative of the solution, as well as the fact that the highest order derivative, which appears in the term in the statement of the partial differential equation, is a third order term that appears here. And there's a Hamiltonian formulation for the Kamasa-Home PDE, because if we take some mass term, which is given by subtracting the solution of the Kamasa-Home PDE minus the second derivative of the solution, we can introduce a system of two Hamiltonians which take this mass term, which is given by this type of transformation from subtracting the solution from its second derivative, which can then allow us to observe that the first integral of the quantity that we're integrating against with respect to the standard Lebesgue measure for the H1 of M term is given by the fact that it's just some quadratic function, because the highest order term that's appearing is some quadratic function of the solution of the Kamasa-Home PDE, as well as resulting from the fact that from the second Hamiltonian of the system, which is also dependent upon the M term, as is the first Hamiltonian H1 of M, we're just taking the integral of some cubic order term that's dependent on the solution in comparison to a quadratic lower order term, which is appearing in the first Hamiltonian. And similar methods by which one can introduce notions of solvability and action angle variables for the Kamasa-Home PD relate to computations with the Poisson bracket for the inhomogeneous six-vertex model, which is to say that we can uncover some different types of characteristics of the Poisson structure from the Poisson bracket of some suitable action angle variables that are parametrized for a different system of interest, namely the six-vertex model with inhomogeneities that we introduced through spectral parameters. And the spectral parameters come into play, and they're important because they're parameters that also enter into the definition and the formulation of the L operator, or some other references also call it the lax operator. And this L operator is important because you can build up recursive relations in the two-dimensional case, which we should also expect to be able to hold in the three-dimensional case for some more complicated L operators that we can just briefly describe the structure of and like kind of very briefly discuss near the end of the presentation once we have established some of the two-dimensional intuition for the L operators and how that factors into the notions of integrability and exact solvability for the inhomogeneous six vertex model in two dimensions. And so the inhomogeneous six vertex model reference that we're going to be making use of, as we've been mentioning in the overview slide from this authors, is the fact that Keating, Reshettikin, and Sridhar, they provide a very interesting approach for looking at integrability of limit shapes in the inhomogeneous six vertex model. And in a previous presentation that I gave, when I was focusing more on the quantum inverse scattering type arguments and methods in only two dimensions, is the fact that this paper, it even relates to another paper by Reshettikin and Sridhar, in which they make use of similar characteristics of the Euler-Lagrange equations in determining whether the cardinality of conserved quantities is either finite or infinite, and how the fact that determining whether the conserved quantities from the solutions to the Euler-Lagrange equation satisfy certain properties helps them conclude some information for the integrability of the limit shape of the inhomogeneous six vertex model. And in the last line of their paper, they raise the possibility and the interest that even though they have some information about the Hamiltonian and they define this Hamiltonian for the inhomogeneous six vertex model, it would be of interest to investigate some other properties and notions of integrability and exact solvability for the six vertex model from other types of arguments relating to the Poisson bracket of the entries of the transfer matrix, and how this would further build upon other properties and exact solvability conditions that the inhomogeneous six vertex model satisfies. And they didn't exactly mention like a difference between the two-dimensional and the three-dimensional model, but as I was continuing to think about this and making connections between how to define transformation matrices and encoding of boundary conditions for a spin chain, a lower and a higher rank spin chain that I've discussed in some other presentations and looked at in some other works, it was just interesting to think about if there would be any type of structure in difference from the L operators for the three-dimensional six vertex model in comparison to those for the two-dimensional six vertex model, and how having information in different qualities or characteristics of the representation of the L operators in the two-dimensional case versus in the three-dimensional case would be interesting, and what would be the changes, if any changes, would there be in the result in computations with the Poisson bracket in the three-dimensional case versus in the two-dimensional case. So this is very much more a simplification in the two-dimensional case versus in the three-dimensional case, because the three-dimensional case with the computations on the Poisson bracket are related to a more complicated system that I'll show later in the slide, as originally derived in the seminal work from Fadiv and Taksha Tan, in which they demonstrated that you can analyze the nonlinear Schrodinger's equation and make use of different computations and properties of the Poisson bracket, and how you can demonstrate that a different class of action angle variables exist for the inhomogeneous six vertex model, which is related to their seminal work and their approach in using the Poisson bracket and looking at L operators and different properties and thermodynamic limits and limit shapes and integrability and so on. So we'll be introducing the model, which is given by the fact that just the regular six vertex model without introducing inhomogeneities to the model through the spectral parameters is given by the fact that it consists of six possible configurations, as well as given that each one of these configurations has to satisfy the condition that about every vertex you have to have two arrows pointing in and two arrows pointing out, which is satisfying the ice rule. And this is also given by the fact that another object which is defined and which is related to a lot of studies of the six vertex model, whether you want to study connectivity properties of different sets of either the strips of the square lattice, the cylinder, or the torus, or crossing probabilities and crossing events on the torus, is given by the fact that it has a height function representation, which I'll be defining a little bit more with some notation in future slides, but we can just describe it really easily because it's given by a function from the faces of the square lattice or the faces of the torus into the integers, in which we can map each one of the faces that the height function resides on by some integer. And depending upon the orientation of the arrow that we have when we pass a certain vertex, the height function will either go up or down by 1. So this is already kind of should be signaling to us that, in a lot of, as in some other previous works and presentations that I've had that I've talked about the 6-vertex model, we can study a lot of different type of connectivity type properties and determine the nature of the crossing probabilities and whether any type of Roussimo or Welsh theory can be used to study specific characteristics and qualities. In particular, for the 6-vertex model, this very much has to relate to the logarithmic delocalization of the height function, which is relating to a balanced variance, which you can define from a balanced probability measure. And besides all of these like characteristics that are going on into the 6-vertex model, it can even have, as we had mentioned, more algebraic or more geometric interpretations, which is very much relating to and interesting from the point of the quantum inverse scattering type arguments. And besides the arrow representation, which is given from the 6-vertex model, we can also have a line representation, which is given in another diagram besides this figure, which was adapted from Dumino, Copan, Carrilla, Manulescu, and Ulamaro's paper on the logarithmic delocalization of the height function for the 6-vertex model. So there are many different types of visual representations, as well as many interesting boundary conditions, whether it be sufficiently flat boundary conditions, slope boundary conditions, or domain wall boundary conditions, which can even be relating to other properties like KPZ universality and how to be able to formulate some type of initial or value problem for a KPZ equation, or as well from the fact that it can be used to relate like interacting particle systems. So there are so many connections even from this model and even from the simplest form that we're taking to define the model from what Pauling had originally been interested in as his main occupation was a chemist. And so we can introduce the model given by the fact that if we want to define it over the torus, we can obtain a probability measure supported over the torus. And for now, we're just going to ignore boundary conditions. But as I just mentioned in the previous slide, there are many different types of boundary conditions for the 6-vertex model, and they can give rise to different qualities and different characteristics of the faces that are contained in the finite volume, namely whether the faces can freeze or not, in which the vertices could all be of the same type within the finite volume that we're looking at. And so the probability measure that's supported over the torus for the 6-vertex model is given by the ratio of W of omega, meaning the weight of some configuration normalized by the partition function of the torus. And then explicitly, if we don't enforce an isotropic parameter choice, the weight of each one of the configurations would be equal to A1 to the N1, A2 to the N2, B1 to the N3, B2 to the N4, C1 to the N5, and C1 to the N6. And besides these basic definitions for the 6-vertex model, as we had mentioned, a lot of different types of characteristics and qualities that appear in the 6-vertex model, and what we would hope to learn about how inhomogeneities appear in the 6-vertex model is relating that we see in the quantum inverse scattering type arguments, or the QSIM type arguments, is given from the fact that we take this disordered parameter, which is delta, which is given by A1 to the A2 plus A3 to the A4 minus A5 to the A6 normalized by 2 times the square root of the first 4 weights of the 6-vertex model, is that we take this quantity be strictly less than -1. And looking at different regions, whether this is -1 or 1 or different related values, it can be related to some conjectured regions of the phase diagram of the 6-vertex model, in which we have a lot of people have discussed in their projects and in their papers how the different phases of whether the material that we're looking at in the 6-vertex model from a configuration is either ferroelectric or antiferroelectric, which can be related to other types of models of statistical mechanics where we try to look at either enforcing order or disorder into the system. And in the presence of 2 external fields, we can introduce the following parameterization for the 6-vertex weights. So which is to say that we're going to enforce some of the characteristics of the isotropic parameters, because The isotropic parameter choice for the six vertex model relates to the fact that we can take A1 and A2 to be A, and B1 and B2 to be equal to B, and C1 and C2 is equal to C. And it's also important because if we take all of these parameters to be one, this is corresponding to the seminal result from Lieb, in which he provided a computation for the residual entropy over on of square ice in his seminal like 70s paper. So it's very much demonstrating how different types of parameters and restrictions and parameterizations that you can put on the weights of the six vertex model, they can interpret what type of thermodynamic interpretation or information you want to glean from the system, as well as we've seen here, you can introduce two external fields like a magnetic field and another field, or just two external fields in general, as well as a strictly positive parameter lambda, which will introduce another parameterization and a type of homogenization of the weights for C1 and C2. And the R matrix for the six vertex model can be constructed with the following, with the two external fields that we gave in the previous slide. And it's given by the fact that all of the diagonal elements are non-empty, they're non-zero. But then the only two elements remaining within the R matrix, which are non-zero, are the C terms, which appear along this smaller anti-diagonal term. And the R matrix will be used because it's going to satisfy Yang-Baxter, but it's going to also help us understand and make use of some information in the three-dimensional case, because the three-dimensional, or the universal R matrix, which is more general, it has more general mathematical structure than the R matrix, which is just given in terms of these two external fields for the six vertex model. It's not going to satisfy all of the same properties that the simpler R matrix does. So the R matrix, the universal R matrix, as we're going to define and juxtapose, again, more towards the end of the presentation, is given in terms of some product of Q exponentials and exponentials of tensor products and other terms, which is a lot different from just this type of expression, in which you can introduce some type of parameterization for the two weights, or for the weights of the six vertex model with two external fields. And as we just mentioned, so this satisfies the Yang-Baxter equation, which is asserting that the equality of two partition functions for the six vertex model. And it's also an intertwining relation, which is relating to a lot of arguments throughout the literature using a quantum zipper argument. And besides the Yang-Baxter equation, there's also a relation for other solutions that are determined by the beta equations, which is relating to the beta ansatz. And there are several different types of ways that one can define the beta equations, whether you also want to look at introducing a dependence of the beta equations on an anisotropy parameter, which also comes into play on spin chains. But in this case, if we're not looking at an anisotropy parameter and we're just looking at spectral parameters V sub k, and other parameters alpha sub j, we can take some strictly positive parameter eta, and we can form a statement of a Yang-Baxter equation that will be satisfied by the R matrix, given by the fact that on the left-hand side of the Yang-Baxter equation, we have this product term from k is equal to 1 to the length of the chain, or to the length of 1 degree of freedom of the finite volume, as a ratio to hyperbolic sines, in addition to the fact that on the next side, we have an exponential of 2 times one of the external fields times the length of the degree of freedom, again, big N. And then we have a remaining product term, which is just given by the fact that M is not equal to J of a ratio of two other hyperbolic sine functions. And the expression for the eigenvalues of the beta equation have the following form. So we can write out some type of expression, which is pretty complicated, it's pretty tricky, but it's just provided, which I thought would be great to reproduce from the reference, and which I'd also included in my preprint, because it's drawing our attention to the fact of the dependence of a product of hyperbolic sine functions that are dependent upon different types of parameters, where the leading order parameter is either eta or eta over 2. And then there are other terms, other lower order terms, which are given by which have a per factor exponential minus nh in comparison to the other term which appears in the statement of the eigenvalue for the beta equation, which is proportional to and has a per factor of exponential of nh instead. And we can define the quantum monodromy matrix from the fact that we know that it's some type of operator that's going to have the following representation, which is to say that we have some position u of the lattice that we're occupying, in the 6-vertex configuration. And we have a collection of local variables corresponding to each site K, which is demonstrating that we incorporate into the definition of the quantum monodromy matrix both a spectral parameter and a local variable corresponding to each site, as well as being a function of the two external fields, which we have been introducing from the parameterization of the 6-vertex model when we chose that we weren't going to have an isotropic parameter choice of weights. And from the quantum monodromy matrix, we can define the transfer matrix, which is given by the fact that we take the trace of the transfer matrix, or the quantum monodromy matrix to obtain the transfer matrix. And we also have a product of n diagonal matrices, which appear in front of the trace of the trace of the quantum monodromy matrix to obtain the transfer matrix, which is also dependent upon, as we had seen here, the spectral parameter and each one of the local variables corresponding to each of the sites K, and also from the fact that it still is dependent upon the two external fields. And as we have been referencing several times, now I wanted to more formally introduce the reference from the seminal work, which I have been describing, in which the authors make use of computations with the Poisson bracket, along with several other things that we have been mentioning and repeating throughout the presentation. So this is the fact that this is a Springer reference, and it's titled Hamiltonian Methods in the Theories of Solitons. So it's of interest to in previous work that I explored to establish that a conjecture due to Reshetikhin or Keating, Reshetikhin, and Sridhar is true for the inhomogeneous 6-vertex model by making use of the technology and the methods in this paper. And in this paper, they're studying the nonlinear Schrodinger's equation. So it's just a typical Schrodinger's equation, but it's in the presence of some parameter chi, which is, I think it's strictly positive. And then we're taking a nonlinearity that we're adding onto the nonlinear Schrodinger's equation, in which we have the absolute value of the solution of the wave function squared times the solution of the wave function that we're expecting to satisfy this new nonlinear PDE. And from the Springer reference, we can compute the action angle variables for the nonlinear Schrodinger's equation, in which the authors provide a large n limit for the quantum monodromy matrix, and they just denote it by T of lambda as big N goes to infinity, and it's given by this product. It's given by the limit in the sense that when we're taking x to positive infinity and y to minus infinity, we have that the quantum monodromy matrix in the large n limit is given by e minus x of lambda times tx y of lambda times ey of lambda. So we incorporate in the first e factor one of the x points that we're letting go to positive infinity, whereas in the other e factor that's just dependent upon y, we're incorporating the other point which we're letting tend to negative infinity. And in the infinite volume limit of the monodromy matrix from the previous slide, the quantity E is dependent upon solutions to the nonlinear Schrodinger's equation and the Pauli matrices, which form a basis for our dynamics and quantum mechanics in general. So this is given by the fact that we look at Ex of lambda, where the Pauli matrix for the Pauli basis, it comes into the seminal work from Pauli, and it's taking the exponential of this matrix. So we're having a matrix exponential for the definition of E in studying and applying this Hamiltonian method and formulation for the nonlinear Schrodinger's equation. And the Hamiltonian formulation for the nonlinear Schrodinger's equation is from solutions to the system in which we can fashion and form a Hamiltonian, which is dependent upon the Hermitian conjugate or the complex conjugate of the field, as well as the wave function, as well as the wave function itself in the position that we're looking at, and which is given by an integral over the state space of the real numbers in terms of the derivative of the wave function with respect to x, the derivative of the complex conjugate of the wave function with respect to x, as well as another part that equals xi, which is some strictly positive parameter. That's another parameter that we incorporate into the definition of the Hamiltonian, and then taking this product of two other wave functions squared. And to compute the action angle variables, of the nonlinear Schrodinger's equation, much like those for the Kamasa-Home PDE that we mentioned at the beginning of the presentation, we need the tensor product of the Poisson bracket. So this is given by the fact that if we take the tensor product between two arguments of the Poisson bracket, when we're taking, say, a transfer matrix of x, y, and lambda and x, y, mu, so two different spectral parameters, lambda and mu, it can be expressed in terms of just taking some R factor as well as pushing over the T of xy of lambda into a tensor product with Txy of mu in the remaining argument for the Poisson bracket. So the tensor product of the Poisson bracket is really important because it helps us from the seminal work look to adapt the work that Fadiv and Tashatan did, on which they looked to obtain a system of relations which allows them to compute the Poisson bracket and characterize properties of the Hamiltonian flow and make conditions or make conclusions with regards to exact solvability and integrability of different systems. So this is more of a quantum mechanical system in physics because the nonlinear Schrodinger's equation, it's like trying to see about what types of properties or characteristics certain particles would satisfy when you constrain them to a certain volume, or where you try to make some conditions or stipulations about how well you can measure the position or the momentum of different particles or ensembles of particles within the system, and how this would relate to like a quantum inverse scattering type approach. And the Poisson bracket can take a few forms, which is given by the fact that we can either just take the Poisson bracket between f and g without taking the tensor product over the argument between these two f and g, the two test functions, or whatever you want to call them, the parameters in the Poisson bracket. And it's given by I to the integral from minus L to L over the real line of subtracting these two mixed partial derivatives together, where we're just looking at either derivatives with respect to the wave function or with respect to the complex conjugate of the wave function, that we're differentiating these functions f and g with respect to. Or we can also have a representation for the tensor, for the Lie bracket, or sorry, for the tensor product in the Poisson bracket, because in the Poisson bracket, in this case, in the second Poisson bracket, we have I times the integral from minus L to L, so the same finite volume, with the fact that we just replace, instead of ordinary multiplication, we replace each one of these arguments with a tensor product and we subtract them, but we still integrate with respect to the standard Lebesgue measure. And when performing our computations we have been discussing and drawing the viewer's attention to for the lower two-dimensional case, with an interest for the three-dimensional six-vertex model and three-dimensional L operators and three-dimensional transfer matrices, we heavily make use of the following properties of the Poisson bracket. So it's given by the fact that the Poisson bracket satisfies anti-commutativity, in which if we take two of the arguments f and g, it's just equal to minus g and f. So just if we interchange the two arguments, we accumulate a minus sign, as well as the fact that the Poisson bracket satisfies a bilinearity condition, which is that if we have some bilinear function which appears with respect to one of the arguments of the Poisson bracket, we can just break it up while maintaining that the other coordinate h will stay the same. And then this works also for just the other coordinate or the other argument of the Poisson bracket. And we can think about how we can make use of these two identities to be able to separate more complicated terms of arguments that we're trying to compute the Poisson bracket of, and then look at how this would help us obtain approximate asymptotic expansions of terms of the Poisson bracket, which will be related to conditions of integrability of the Hamiltonian for the inhomogeneous six-vertex model in 2 dimensions. And then if we want to look at some 3-dimensional representation of the six-vertex model, we can still make similar uses of the Poisson bracket, but that there will be more relations and more computations rather than the 9 Poisson brackets, which are computed for one of the relations. And this will make our lives more complicated, but at the same time, it'll help us be able to characterize more different characteristics and structures of the 3-dimensional six-vertex model to determine what notions of integrability and exact solvability would hold or carry over to a higher dimensional model, if we enforce some similar type or a higher dimensional analog of boundary conditions. And the third property is given by Leibniz's rule, which is given by the fact that if we have two product of two functions in the first argument in the Poisson bracket, then we can write it in terms of taking one of the arguments out and multiplying it to the left of this argument G with the Poisson bracket FH, or as well as taking F and multiplying it to the right of the Poisson bracket G and H, as well as a Jacobi identity, which is just given by the fact that if we take any of the terms on the Poisson bracket, we can embed an additional Poisson bracket within one of the arguments for a larger, broader Poisson bracket with two of the test functions that we have, and we can do this type of permutation. It's like some identities which appear in Riemannian geometry and other areas for general relativity. So it kind of shows up here with the Poisson bracket. And the higher dimensional transfer matrices and boundary conditions and L operators all come into play from this work, as we have been mentioning. So it's very much of interest to determine, what are the limits of the two-dimensional L operators in applying this approach, and what types of complications would we encounter rather than, some expected complications from, scaling up the dimensionality of the L operator by one. And as we have been mentioning, some considerations which we have to take into mind are that higher dimensional L operators are constructed from higher dimensional matrices, which implies that the recursive relations from the product of L operators should depend upon an additional spectral parameter. So this is relating to the fact that if we're looking at a three-dimensional type representation for the six vertex model, we can specify three spectral parameters for each dimension of freedom. And, we can vary the spectral parameters a little about 1 degree of freedom while holding another coordinate fixed and vary further and then vary in the remaining degree of freedom. So we have to very much keep track of all of the types of spectral parameters which we can take for making sense of some type of higher dimensional large N limit for the quantum monodromy matrix. And we're not going to define those higher dimensional objects in this presentation or this part of this series, because we were just interested in formulating more of the ideas and the notions for the two-dimensional case, but it very much still builds on the two-dimensional case, even though we have some more complicated characteristics about three-dimensional ice in comparison to the qualities and characteristics of two-dimensional ice. And so to this point, as we've been saying, three-dimensional ice, i.e. the three-dimensional six-vertex model, has additional possible configurations from an additional arrow that can point either inwards or outwards to each vertex of the configuration over the triangular lattice. And hence, a broader set of relations must be computed from the entries of the three-dimensional transfer matrices with the Poisson bracket for concluding that suitable action angle variable or coordinates or weaker properties, or whether similar types of properties exist at all, for proving that the Hamiltonian flow is integrable. And additional considerations come from the fact that for arguments on the quantum inverse scattering type method for the nonlinear Schrodinger's equations, computations with the Poisson bracket can be simplified depending upon entries of the transfer matrix, which yields approximate expressions for the Poisson bracket of entries of the transfer matrix. And as we had mentioned, from the properties of the Poisson bracket that were given earlier, Leibniz's rule, which is one of the properties of the Poisson bracket that was previously described, is used several times for computations of 9 Poisson brackets for re-expressing entries of the transfer matrix and providing some asymptotic expansion in the large N limit for what the entries of the transfer matrix would be. And the QISM type approach and types of approaches is robust and flexible enough to accommodate higher dimensional L operators, transfer matrices and boundary conditions of the six-vertex model, in addition to the influence and homogeneities, which are still of interest for several related models besides the three-dimensional six-vertex model. And the references that we're going to just give an idea is that we can adapt a higher dimensional QSISM type approach and argument from this reference, which provides characteristics and qualities of the universal R matrix. And so this is given from the fact that, as we had alluded to much earlier in the presentation, we can define a simpler R matrix, but the universal R matrix is given by a product of these four factors, in which it appears on page 34 of the reference I gave in the previous slide. And it's interesting for us and helpful because one looks to carry out similar computations between entries of the transfer matrix between underlying assumptions on the R matrix, in which we have Q exponential factors, 3 of them in fact, and as well as the exponential of a tensor product. And I'm not going to be defining everything explicitly now, but rather just describing some more general characteristics, which the exact formulas and more expressions will be provided in the next presentation in the series. But this is given by the fact that if you look at this representation for the universal R matrix for the three-dimensional six-vertex model, there is also corresponding a class of L operators which hold up to Dynkin automorphism. So there's this automorphism action which can give you a family of L operators, and the authors in that universal, exercises with the universal R matrix paper, they draw our attention to the fact that they just wrote down two of them, but in fact, you can write down a whole family of L operators. So it's just demonstrating that, in a sense, in several ways, you can exert a type of generalization and look at more complicated ways in higher dimensional cases and generalizations that would be relating to the three-dimensional six-vertex model, and how this can be viewed as a simplification, or and how the two-dimensional case can be viewed as a simplification of the three-dimensional case with this universal R matrix, which is given by an additional it's defined, this universal R matrix keeps track of interactions in an additional degree of freedom in three dimensions rather than only in two dimensions. But it's also given by the fact that if we look at all of the entries, we haven't defined these precisely yet. But I'll give the viewers some type of hint about how this will come into play of applying a quantum inverse scattering type approach, in which several of these maps, which appear as C, they're maps into a unital associative algebra, which is given by the fact that this already lends the three-dimensional six-vertex model to several different types of algebraic combinatorial and algebraic geometry perspectives, which can even be, which we're even going to discuss in another presentation from double Grothendieck polynomials, and how these can be related to the partition function of the six-vertex model, and how this relates to coloring of the six-vertex model. So it's demonstrating more of a connection between the representation theory, the combinatorics, and the geometry, in terms of how this can be related to higher dimensional L operators and transfer matrices and quantum monodromy matrices, which are used for demonstrating that some type of exact solvability or integrability property holds. And this is just reiterating what we had just mentioned, in that we can see that some entries of this three-dimensional, 3x3 L operator, which is obtained as one of the L operators which holds up to Dynkin automorphism from within the entire family of L operators, is given by a mapping into a unital associative algebra. So there's already some type of geometric or algebraic type interpretation, and even a combinatorial interpretation from symmetric functions or other special types of polynomials and functions, which we don't have in the lower two-dimensional case. So the task of interest for us is that we want to develop higher dimensional relations from L operators for the three-dimensional six-vertex model from information on L operators like we have been talking about for the two-dimensional six-vertex model. And we can carry over, in some cases, some notions from the three-dimensionality of the L operator to the transfer and quantum monodromy matrices. And this will help us determine how notions of integrability change in three dimensions compared to notions of integrability and, in fact, uncolored integrability, because the inhomogeneous six-vertex model was not colored in two dimensions. And this can also further comment upon how aspects of representation theory and the notion of up to Dynkin automorphism influence the structure of the L operator. So the concluding remarks that we have is that we provided an overview of objects for a QISM type approach, including R matrix, L operator, encoding boundary conditions, transfer matrix, and quantum monodromy matrix. And the relations from the L operator undoubtedly become much more complicated in three dimensions for QSIM type arguments from the additional structure introduced in the L operator a few slides ago, namely the algebraic interpretation of some of the entries which appear in the three-dimensional L operator. And the next presentation in this series will describe further computations leading to properties of the Poisson bracket in two dimensions, along with how this information can be leveraged for a QSIM type approach in three dimensions. And thanks for watching.